Hi students. So in previous video we have seen about the de Broglie wavelength of electron. So in order to verify whether the de Broglie wavelength of electron is equal to 1.65 angstrom like that, so Germer and Davisson has proved it. Yes, always these particles they behave like a wave, or they are associated with waves like that, right? So for that they used a method. Whenever electrons are accelerated, or whenever the electron beams are moving with a velocity like that, and if they pass through any crystalline solids, here they use a single nickel crystal, right? So whenever the electrons or charged particles move inside a crystalline solids, those crystalline solids behave like a PTG, that is plane transmission grating, or a diffraction grating element. So what is meant by PTG or diffraction grating? See, when I take a transparent sheet, that is a glass sheet, right? And then using a diamond cutter, if some lines are put using the diamond cutter, so that these lines are called rulings, or they are also called as the opaque portion in this grating element, right? This is what we call as the grating element. Now we can draw even 6,000 lines per centimeter using a diamond cutter or a diamond pointer, right? Now, between each ruling there lies a small space which has the same width of the cutted portion or the ruling portion, right? So the width of that ruling and the transparent portion are same. That transparent portion is called as a slit. So whenever light passes through this type of grating, diffraction grating element, what happens? The light rays will be diffracted. That is, it bend around the edges of the obstacle. Here the obstacles are the rulings, which are the opaque portions, right? So this is what we call as a diffracting grating, like that. Likewise, the crystalline solids like nickel crystal, they are also acting like this grating element, that is diffracting grating element. So whenever electron beam passes through the nickel crystal, so what happens? The layer of the atoms, right, acts like the space between the atoms behaves like a transparent portion, that is a slit portion, and those atoms, they are arranged in series, right, like that. So they act as the opaque portion, so making the electrons to get scattered. So how the electrons are getting scattered? For example, if the atoms are arranged like this in the nickel crystal, so the space, this region, right, so act as, actually here this region, this space and the thickness of this region will be same, but my diagram doesn't show like that. It hasn't been drawn like that, so don't mistake. Actually the width will be same. So now this portion act as the slit portion, this portion act as the ruling, that is that opaque portion. So here, whenever light enters through this transparent portion, there will be bend like this or bend like this, okay, in this direction or in this direction. Not the light rays, here the electron beams, okay. Now, due to which here the electron beam will be, or the energy of the electron beam will be absorbed and then re-radiated. That is, initially the frequency or wavelength of the electron beam will be something, and after being absorbed and then re-radiated, that is, re-radiated means it is given out with some other change in their wavelength, or frequency. So there will be a change in frequency or wavelength of the electron after they have come out of this that is the opaque portion. Now, after it has come out, so what happens? They are reflected back. So they will be reflected, that is, and then while they are reflected, they will be scattered in different directions. So scattering here means, so whenever the light rays are absorbed by the particles present in the atmosphere, so initially the frequency of that light rays will be something, but after absorption, and then it will be re-radiated. Again, the light rays will be re-radiated, that is, it is given out. So whenever they are re-radiated out, they will come out with some other frequency, and this is what we call as the scattering of light rays. Like that, here scattering of electron beam occurs. It means the light ray which has been reflected by these atoms, because the atom contains mostly of the electrons. So the electron beam is negatively charged particles. Even the electrons in the atoms, they are also negatively charged particles, due to which repulsion takes place, and due to this repulsion they will be reflected and come out of the crystal and scattered. So that is why they say that the electron beam will be scattered by the nickel crystal, and whenever they are scattered, they will be scattered in different directions, and that scattered electron beam will be measured, that is taken by the detector called that electron beam detector. So that will measure the intensity of the scattered electron beam, right? Now we are going to see that Davisson Germer experiment. Right. So this is simple skeletal structure of that device. Here they are using low tension battery. So low tension here means the resistance, because force, tension, resistance, they are all load, they are all same. So here in electricity, that tension is called as the resistance. So low resistance battery. So low resistance means high current will be there. Whenever high current passes through this filament, thin filament, right? Like what we will see in the bulb, right? Tungsten filament like. So they'll be heated. So due to this heating effect, now what happens? Thermionic emission process will happen in this. So the thermionic emission means due to the heat energy, now electrons will be ejected out of the atoms. So this electron will be converted into a beam-like structure, right? Beam-like thing, and then the electron beam will be ejected out, coming out of this filament. Here another battery, that is HT battery, which supplies a high voltage between the filament and this aluminum cylinder. So a high voltage is given to this electron beam between this filament and the aluminum cylinder. Now this high voltage, so this is high tension. High tension means high resistance. If resistance increases, then current will be less, voltage will be more, right? So this high voltage is used to accelerate the electron beam, that is charged beam, right? Now here two thin aluminum diaphragms are kept, right? So in between this filament and the aluminum cylinder, so this will look like a disc-like structure with holes. So through this hole, the electron beam enters. So this is the hole, okay, and these are the thin aluminum diaphragms. So which collimate, that is, which will be used to send the beam in a parallel way, right? So there will be no deviation like that. So because the beam has been accelerated by this high tension battery, so in order to avoid any deflection, these diaphragms are used, right, to send them as a collimated beam. Now after passing through the aluminum cylinder and then it reaches the nickel crystal, here whatever the thing previously I said, no, that is happening here. So the electrons will be absorbed, re-radiated, and here it is, they are all reflected, the electron beam will be reflected, and while they are reflecting out from the nickel crystal, single crystal, so they will be scattered in different directions. So here that will be collected by the beam detector, right? This detector moves like this on this plane of the board. So the theta can be changed, right? Like that. So at last, after collecting all the intensity of the scattered electron beam is measured. So from this, they draw a graph. Here, y-axis intensity, x-axis is the angle theta. So at an angle of 50 degree, if a voltage of some 54 volt is given to this electron beam, here a voltage of, that is the accelerating voltage of 54 volt is given to the electron beam. Now at an angle of 50 degree, the intensity of the electron beam reaches a maximum value. It shows that the diffracted, so here the diffraction is happening inside, so the diffracted and also the scattered electron beam will have a constructive interference, right? Because the intensity is maximum here. Now, and I said at an angle of 50 degree, that too, when the accelerating voltage is 54 volt, this intensity reaches the maximum value like this. Right? At last, after substituting the value of the 54 volt in the de Broglie wavelength, that is lambda equal to 12.27 by root 54 angstrom, the value shown was 1.67 angstrom, which is nearly equal to the de Broglie wavelength of an electron, which behaves like a wave whenever they move around the nucleus, right? So using which it was confirmed that always the matter waves or that is the electrons behaves like a wave. So the value of the de Broglie wavelength of this, after substituting the value of 54 volt here, it was nearly equal to the value of the original, that is the real value of the de Broglie wavelength of the electron. that is 1.65 angstrom. I think you would have understood the concepts. Thank you.